Hello everybody, welcome to the subject electromagnetic waves and transmission lines. In this video, I am going to discuss about reflection by a perfect dielectric at oblique instance. Oblique instance is nothing but it is also called as plane of incidence, which is defined as a plane containing propagation of the incident wave and a unit normal vector to the boundary. So there are two cases of plane of incidence. First one is parallel polarization, which can also be called as vertical polarization, in which the electric field vector of an incident wave is parallel to the plane of incidence. And another case is perpendicular polarization, which can also be called as horizontal polarization, in which the electric field vector of an incident wave is perpendicular to the plane of incidence. You can see in this figure. So here we are considering two dielectric media, medium 1 and medium 2, which are separated by the boundary. Here, when the wave is incident in the medium 1, some part of the wave is transmitted into medium 2 and some part of the wave is reflected into the medium 1. So when you say it is a parallel polarization is when the electric field vector is parallel to this plane of incidence. This is a plane of incidence which consists of incident wave and unit normal vector. This is the boundary or the interface where this is normal to this unit vector. So this is a normal vector which is normal to the boundary. So this is the plane of incidence which consists of incident wave and plane of unit vector, unit normal vector. So to this plane of incidence, the electric field vector of the incident wave is tangential or parallel to the plane of incidence. Then it is said to be parallel polarization. And coming to perpendicular polarization, here you can see the plane of incidence. In the plane of incidence, the electric field is perpendicular to the plane of incidence. The electric field vector of the incident wave is perpendicular to the plane of incidence. That is, the magnetic field is tangential or parallel to the plane of incidence. And coming to parallel polarization, here you can see when the wave is incident towards the boundary, some part is reflected and some part of the wave is transmitted into the medium 2. So during reflection, the phase of the electric field vector of the reflected wave is changes. Whereas in the perpendicular polarization, there will be no change in the direction of the electric field of a reflected wave. Okay, this is about the two types of oblique incidence. Now, the main aim is to determine the transmission coefficient and reflection coefficient when the wave is incident obliquely towards the boundary under these two cases. So now let us see here. Remember always that electric field and magnetic field are perpendicular to each other or at right angles to each other. In such case, the power transmitted per square meter will be equal to the square of the electric field divided by the impedance of the medium, E square by eta. In oblique instance, when the wave is incident on dielectric, a part of the reflected and a part of it is transmitted through the dielectric. Now here I am going to define the angles, that is theta I, theta R and theta T are the angles of the incident, reflected and transmitted rays, where the angle of incidence is equal to angle of reflection. This can be defined according to the law of reflection. And the angles theta I, that is the incident angle, and theta T is the transmitted angle, are related by Snell's law, that is sin theta I by sin theta T is equal to square root of the permittivity of the medium 2 to that of relative permittivity of the medium 1. So now let us see the first case, that is parallel polarization, and let us determine the reflection coefficient and transmission coefficient. You can see this is the boundary which is taken along. It is the interface between the two medium. This is medium 1 and medium 2, which are separated by the boundary which is taken along x direction, and this is the unit normal vector to the boundary. Okay, so when the wave is incident at an oblique angle, that is at an angle of theta I, some part of the wave is transmitted into the medium 2 and some part of the wave is transmitted into the medium 1. Now, as I told, in parallel polarization, the electric field vector is parallel to the plane of incidence, and but it is normal to the direction of incident wave. Here direction of incident wave, here you see this is the electric field vector of the incident wave, which is perpendicular to the direction of the incident wave, but it is parallel to the plane of incidence. So here the electric field vector components are resolved into two orthogonal components. One component will be tangential to the boundary, other component will be normal to the boundary. So here in this diagram, here you can see this is the tangential component. Actually here the printing mistake is that this is EI cos theta I. This is the incident wave. EI cos theta I becomes the tangential component to across the boundary, and EI sin theta I becomes a normal component to the boundary. Okay, similarly, the electric field vector component of the reflected wave also is resolved into two orthogonal components. One component which is parallel to the boundary, other component normal to the boundary. And similarly, in the transmitted, in the medium 2, the transmitted, the electric field vector of the transmitted wave is resolved into two orthogonal components. One component along the boundary, another component is normal to the boundary. So here, now according to boundary condition, the tangential components across the boundary in medium 1 will be EI cos theta I and ER cos theta I, because here angle of incidence is equal to angle of refraction. So theta I is equal to theta T. That is what we have taken here in parallel polarization. So here, when coming to the tangential component across the boundary in medium 2 becomes ER cos theta T. So let us see here. So in the case of polarization, the electric field vector components which are parallel to the reflecting surface require to be continuous across the interface. So continuous across the interface means E tan 1 should be equal to E tan 2. So the tangential component across the boundary in the medium 1 becomes EI cos theta I is equal to ER cos theta I. So instead here in this notation, instead of theta I, angle of incidence are taken as a theta 1, and transmitted wave, the angle of transmitted wave is taken as theta 2. Please note it down in this difference. And here this is the total tangential electric field component across the boundary in the medium 1, EI cos theta 1 minus ER cos theta 1. So this minus sign indicates that the direction of the electric field vector of the reflected wave is changing. So this is equal to tangential component across the medium 2, ET cos theta 2. So the intention is we have to calculate the reflection coefficient. So what is the reflection coefficient? Is the ratio of reflected wave to that of incident wave. So on simplification, ER by EI, this is the reflection coefficient for parallel polarization. This is what you are going to obtain, where eta 1 and eta 2 are the impedance of the medium 1 and medium 2. Since it's a perfect dielectric, so there the conductivity is 0 and the permeability is taken as mu1 equal to mu2 equal to mu, and as a result the intrinsic impedance of medium 1 and medium 2 can be written as root of mu by epsilon 1 and root of mu by epsilon 2. So now you substitute these values in this expression, you get reflection coefficient for parallel polarization. The final answer you are going to get like this. Okay, by using the Snell's law, root of epsilon 1 sin theta 1 is equal to root of epsilon 2 sin theta 2. After considering the Snell's law, Also, finally, you get the expression like this. Now, if you want to calculate the transmission coefficient is nothing but it's the ratio of transmitted wave to that of incident wave. So here 1 plus transmission coefficient, 1 plus reflection coefficient will be nothing but equal to transmission coefficient. Using that relation, you can calculate the transmission coefficient for the parallel polarization. So this is the expression for parallel polarization. I am leaving as an assignment to you. You substitute for eta 1 and eta 2 root of mu by epsilon 1 root of mu by epsilon 2 and get the expression in terms of permittivity like this, as you got for the reflection coefficient. So these are the expressions for reflection coefficient and transmission coefficient for parallel polarization. Now coming to perpendicular polarization. Here in perpendicular polarization, the electric field vector is perpendicular to the plane of incidence, but the magnetic field is tangential to the plane of incidence. Here, for each wave, the tangential component of the magnetic field is resolved into two orthogonal components. One component tangential to the boundary, other components are uh, perpendicular to the boundary. And there will be no change in the direction of electric field vectors. So according to the boundary conditions, the tangential component should be continuous across the interface or the boundary. So EI plus ER is equal to ET. So from this ET by ER, here I am going to take EI as common. This expression becomes ET by EI is equal to 1 plus ER by EI. So this expression comes according to law of conservation of energy, where the energy of the incident wave is equal to the sum of energy of the reflected wave plus energy of the transmitted wave. So using that law of conservation, here I didn't mention, using that law of conservation of the energy, you get this expression. On simplification, the reflection coefficient for perpendicular polarization, you are going to get the expression like this. Here it is shown in this equation. So and because it's a perfect dielectric for the lossless medium, the impedances are replaced by root of eta 1 is equal to root of mu by epsilon 1 and eta 2 is equal to root of mu by epsilon 2. So you get the expression for reflection coefficient. This is the final expression what you are going to obtain on simplification. So this is the reflection coefficient for perpendicular polarization, and once you obtain the reflection coefficient for perpendicular polarization, you can obtain transmission coefficient by using this relation. 1 plus reflection coefficient is equal to transmission coefficient. Again, I left to the exercise for you to express this transmission coefficient in terms of permittivity of the medium. Okay, these are the expressions what we have obtained for parallel polarization and perpendicular polarization. Now next coming to another definition, that is Brewster angle. So this Brewster angle is nothing but it is defined as angle of incidence at which no reflection takes place. So let us find the Brewster angle for parallel polarization. If the angle of incidence is equal to Brewster angle, that is when the reflection coefficient is equal to 0, then the Brewster angle, on simplification, you consider the reflection coefficient expression for a parallel polarization and substitute for equate to 0 and substitute for theta is equal to theta. On simplification, you get this is the Brewster angle, tan theta b is equal to root of epsilon 2 by epsilon 1. This is the Brewster angle what you obtain when no reflection takes place in parallel polarization. So this value is practically possible for not only lossless media but for non-magnetic materials as well. And when you come in case, when you see in the case of perpendicular polarization, if there is no reflection, it implies that total transmission takes place. And for you consider the expression for reflection coefficient for perpendicular polarization and equate to 0. On simplification, you get tan theta b is equal to root of mu 2 by mu 1, where it is expressed in terms of permeability. Where it is theoretically it is possible, but practically it is quite difficult. We consider only a Brewster angle at parallel polarization. Next, coming to total internal reflection. When you say when the total internal reflection takes place when the wave is traveling from denser medium to rare medium. That is, here let me consider medium 1 and medium 2, where medium 1 is a denser medium and medium 2 is a rare medium. Here, that means the permittivity of the medium 1 is greater than permittivity of the medium 2. Under this condition, the angle of transmission becomes greater than the angle of incident wave. Angle of incidence wave. So when the angle of the transmitted wave is exactly pi by 2, that is 90 degrees, then the transmitted wave is aligned along the interface. You can see here exactly at theta is equal to pi by 2, the transmitted wave will be aligned across the interface or the boundary. You see in this diagram. Still, when theta I, the angle of incidence is further increased, there is no transmitted wave. So, no wave will be transmitted. So, the complete wave will be reflected back into the medium one. This is called total internal reflection. So, the angle at which the total internal reflection takes place is called critical angle. That is theta I is equal to theta C. That is, this is obtained when theta T transmitted angle is pi by 2 and angle of incidence is equal to critical angle, and using Snell's law you sin theta T by sin theta I is equal to root of epsilon 1 by epsilon 2. You substitute for theta T is equal to pi by 2 and theta C, I is equal to theta C. You get the critical angle at which the total reflection takes place. That is, the critical angle of incidence is equal to critical angle, which is equal to sine inverse of root of epsilon 2 by epsilon 1. So, this is the angle of incidence or the critical angle at which the total internal reflection takes place. Okay. Thank you.